Hello everyone and welcome to We Meet at Digital Days. My name is Lisa Richter and I will moderate this presentation. We are very pleased that you took the time to participate in our virtual conference. The topic of this presentation is how to simplify your USB-C DCDC project using OnSemi reference design. Our speaker is Andrew Yule. He is from On Semiconductor and we are really happy to have him here today. He will hold the presentation and will answer your questions afterwards. Before we start, I would like to point out one thing. You will be muted during the presentation. This means that you cannot ask questions via microphone during the presentation. Nevertheless, you have the opportunity to ask questions during the presentation at any time via the chat function. You will find the chat function in the control panel. This presentation will be about 30 minutes long. The chat questions will be answered in a Q&A session following the webinar. There are 5 to 10 minutes in addition scheduled for this. If we are unable to answer all of your questions within this time, we will answer them via email afterwards. If you still have any other questions left, just mail us at exhibition@we-online.com. We will try to answer all of your questions promptly. At the end of the webinar, you'll be asked to participate in a feedback survey. We would be pleased if you take the time to fill out the survey and help us to improve our event. You'll receive the link to the presentation in the next few days, and the recording will be available at our website shortly. Now I will hand over to our speaker, and I wish you an exciting presentation.
Hello, my name is Andrew, and I'm going to present today about how to simplify USB-C DCDC project using OnSemi reference design. So the first one, we have the reference board, which is having both two the large chips. The one is NCB81599, which is a DC-DC buck boost. Another one is FPUSB 3307. So this board provides for the USB Type-C applications for the PD, and also with the buck and boost applications. So this reference board is pretty simple, just taking power, DC power on the left side, and also and then the output on the Type-C port, it supports all the powers like 5 volt and 5, 9 up to 20 volt. And this board is a 60 watt. So this reference board is for the automotive single port application purposes. And the USB PD is widely spreading these days from the USB Type A port. And so as more, the interests are on the USB-C port, especially in the automotive applications. So this board also supports the PD and up to the USB PD, the PPS, which means programmable power supply. And next slide, I will talk about more. Okay, so this reference board is composed of 2 parts largely. So one is NCB81599. This is port switch buck boost. So it controls all the 4 FETs or NFETs externally, 2 for the buck operation and 2 for the boost operations. And that is interfacing with the FPUSB 3307, and 3307 is interfacing Type-C and Type-C ports over the CC1 and CC2 and the B-bus path. So with the Type-C connector, the sync device is detected over the CC1 and CC2, and then if sync is attached, then the B-bus is supplied, and the first B-bus is going to be 5 volt according to the USB PD spec, and the B-bus, the voltage is controlled by the 3307, and it is feedback to the 81599. So the power is fully controlled by FPUSB3207, which is a standalone state machine based. So it's pretty simple because there is no MCU control, which means no software control is needed. So FPUSB3207 controls all the USB PD and the Type-C applications. And the NCB 81599 takes the power supply portions based on the battery power between the 4.5 to 32 volts input. So this is a simple schematics. As you see, NCB 8159 block, so that handles the two FETs for in the front side with the series register. This is the current sense 5 milliohms, and actually there are another 5 milliohms on the output side with on the booster side. So there is a booster FET, and the inductor is for the switching operation in between. And FPUSB3207 interfaces to a Type-C port over the CC and the D plus and D minus. So D plus and D minus takes the charger type detection for the sync device. Actually, there is no USB data transactions, but it is for charger type detection. And sync device is detected by CC, and the B-bus path is controlled by another FET that is controlled by gate pin of the 3207, controls the gate with the sync attached. So once the sync device is attached, then the 3207 detects the sync and then turns on the gate of the NFET. So then the B-bus will be provided to the sync device. And also the cat pin of the 3207 feedbacks to 599, which is through the comp pin of the device. So then this voltage of the B-bus is controlled by comp of the 8159 through the cat pin. So that is a power feedback depending on the sync request. And all the others are in detail. Schematics are in our reference document in the later. So this is small size, the 45 millimeter and 45 by 75 millimeter, small one. And this red box is from the Würth components. So some this Type-C connector and inductor from the Würth, and this is the for power input from the external power supply, and this is a specific connector for our Strata interface, which is I'm going to explain more later slide. So this is an internal debugging and internal or software development port. This is in detail the layout. So Type-C connector is located in here, and the inductor is in between, and the 81599 in the middle for the buck boost. So two FETs, and this is for buck operation, and this is for boost. And this is the left one is input side power. So yes, the filter inductor and the reverse blocking FET. And Strata connector, and we have two pads for FPUSB3207, one for the smaller package. We have actually two different packages, and another one is a little SOIC, a little large. And actually, there are three RSense 5 million sensor register. Two sensor register on the high side. This is B-bus path. And another one is RSense is for the low side, the ground return. So this, the return current is measured by the FPUSB3207. And so this current for this, the OCP or yes, OCP or the current limit is controlled by FPUSB3207. So here is the BOM, the parts of the board from the Würth. So as we stated about, the Würth parts take important role because the DC-DC and the Type-C applications. So in the DC-DC part, in Inductor, we are using the Würth parts. I see actually a lot of the Würth parts, Würth Inductor in other application, the reference board too. So, and USB connector, I'm in the next slide, it's going to be in detail, and it's more stable parts. So rather than other competitors. And the capacitors are above actually alternative parts from the Würth. And actually we need the automotive applications. So we prefer the automotive qualified unit. The Würth parts are a lot of used in the ON because this is a Strata. Strata, I already explained that. Strata is standard development form in ON. So every single part, we have many reference board, and many boards have the Strata interface, and there are and all of them have the connectors, and all the connectors from the Würth assembled. And also I see the inductor in other reference board, the PAN 6500 part. So there is that, and I actually use this the Würth the sample box, capacitor sample box in the lab. So I always search the capacitors from the Würth sample box if I need it. That's so that's one of my favorite. This is comparing of the Type-C connector. The left one is from Würth that I'm using in the reference board. So in this connector, the better one is actually the tight holding the PCB with the deep lines, and also the second laws are visible on the PCB. So it's easier to debug if there is any issues. The right one is the competitor one. Actually, I've been using in another EVB lately, and I had some issues about this connector because in the Lipro station, the solder cream was not much on the second law. So the only actually the CC1 is on the outside, and CC2 is on the second row. So one CC line was not working in my evaluation kit. So I suspected the connector, and so I found some issues with that. Also, this connector type has only the 4 deep pins. So the holding power was not stronger than the Würth. So I prefer personally the Würth parts, the Type-C connectors. And this is the waveform of the reference board. We see the V-bus changing from the sync request, the V-bus from 5 volt to 15 or 15 to 5 volt, and the yellow and the blue lines are switching waveforms of the boost and the buck and boost, because the input voltage is 12 volt. So at 5 volt is going to be buck mode, and the 15 volt it is boost mode. So it's automatically changing the mode. This is another case. The V-bus is 20 volt and the V-bus down to 3.3 volt. This is the minimum voltage of the USB PD. So and then we see the switching mode change in between the buck and boost. This is the other way, 3.3 to 20 volt. And here is the efficiency data. It's almost always over 90% in case the voltage is 9 to 20 volt. But this is at 5 volt is going to be lower because the input voltage is 12 and the buck mode. So this is natural. And but the other case is pretty good efficiency at above 95%, up to 3 amps load. This is explaining the buck and boost dynamic change depending on the voltage request. The 81599 controls the external 4 FETs, S1, S2, and 3, 4. This is for the buck, and this is for boost. So all the mode change operates based on the feedback from the FUSB 3307. Like you see, FUSB 3307 controls the cat pin. This is feedback line control to 8159 in case the voltage change is required. So when the voltage, the V bus is needed to 20 to 5, then the V cat pin controls the more current sinking to the inside. Then the cat pin, the voltage is going to change. So then the comp pin of the 8159 changing the voltage, then internal circuits of the 8159 changes the internal mode from the buck and boost, depending on this feedback. Also, the internal DAC. So there is internal DAC, so that controls the voltage too. So this is one of the critical thing in the PCB layout. So for the current sense, we recommend that PCB layout like internally, because this is Kelvin sensing. So this current sensing is pretty important because our device, our reference board limits the current like 2.5 amps or 3 amps. Then we have to limit the exact current. So we sense the current, the load current based on this layout. But if in case of a bad layout, if the sensor line is external, it's a long layout like this one, so the resistance value can be changed, like not just 5 milliohms, it can be 6 milliohm or 7 milliohms. Then the sense current is gonna be changed. So then our device is gonna make a OCP at 2 amps or 2.5 amps instead of 3 amps. So it's going to be lower the current limit too. So we recommend this type of current sense layout, and this is the reference board of layout. So we see that the current sense layout is like this way, internally and cautiously. So it's good one. And this is thermal data of the reference board. And so as we see at the left one is 5 volt 3 amps, the top right is the very right is 20 volt and 3 amps. So the temperature is a little higher, and we see depending on the mode, in the buck side or booster side, the FET temperature is going high, and the inductor, actually the inductor is the 7 milliohms DC, so and the DSR, so the temperature is going high too. So because this board is a 4-layer the PCB, and so pretty compact and small size, so temperature is a little high at the maximum power 60 watt, and this is boost operating. And so but it's like this temperature is high, but it can be controllable. So this is the summary of the benefit of the reference board. So the first of this reference board, the first thing is no MCU needed. Only a USB 3307 takes all the Type-C and PD portion. And I'm sorry, this is NCP or NCB. NCB 81599 takes the power side. So very easy to implement, only supplying DC power to the board, then it automatically works everything, no software. And we also passed all the USB PD compliance testing, so our interrupt testing. So this board is going to work all other the off the market devices, having the USB PD port. So this is also good for the automotive applications. And this board supports the short protections like a CC1, CC2, up to 26 volt tolerance DC. Over voltage, over current, and the low voltage protections are integrated, and also the over temperature protections. Over temperature protections is set to about 110 degrees. And internal, the bleed circuit is on B bus. So if there is when the cable is plugged out or B bus drops down, then the internal bleed circuit is turning on and activated. So Strata is the standard company standard the development studio, and this is connector through from the Würth. We have a Strata board that is provided for development. But actually, this board is working standalone, but this has the Strata interface that is to provide the V-bus or some of these informations like the voltage of the V-bus and the load current and the input voltage. So for this information, some extra circuit is implemented on the board. So this Strata board has an MCU, and that is interfacing with the PC for this GUI. So graphic user interface is supplied. And so this MCU on the Strata takes all this data from the board. So this is easy to debug or just for the verifying the status of the board. But this, even though this board is working standalone. So there are a couple of ways to verify the board. So this small board is the reference board we made with, and then the small one is FUSB 302B board. So which support sync and the USB, the PDDRP. So if two boards are connected, then this is going to be a sync, and this reference board is going to be power source. And the USB 302 supports the PC GUI. So so in this PC there is GUI for the USB 302, and that shows the interface of the USB traffics. So that's good one too. And another way to use traffic verification is using USB snippers like source caps. We see this way. So there is the reference board that is interfacing through the snipper and then the laptop. So then from the snipper GUI, there is a source caps and a request like all these the PD traffics. This is a simple USB PD contract. The left one is the reference board side operation. The right one is the sync device operations. When the Type-C cable is plugged in, we send the reference board and the source capabilities to the PD message, and then the sync requests the power that needs. So then it's gonna send the accept or reject to the sync, and then the PD, and then if the PS ready message is sent to the sync. And the USB PD PPS is a programmable power supply, we mean. So this is from the GUI from the FUSB 302. And there is the default of the reference board has a USB PPS, the power APBS. So and here we can see a 3.3 volt to a 21 volt. So this power is available from 3307, the reference board. So if a sync requests any voltage in between, like a 3.3 or 3.5 or 3.6, then the voltage is supplied to the sync from the reference board. So Also, the current, it can be requested like a 2.5 or 2 amps, any for the current limit when the current limit is needed. So it depends on the sink request, but also the yes, depending on the sink request, the source, the reference board provides all the powers. So the purpose of the PPS is for direct charging. We say it's bypass charging. So in the left, there is a reference board. On the right side, if the battery is a 2S, like a 1S, like a 2S or 3S, that needs about 9 volt or 10 volt charging, then the sink device can request the 9 volt or 10 volt or any voltage that needs, including the IR drop. So then in case like 9.5 volt or 2 amps, then this board is gonna support direct the 9 volt and with the 2 amps current limit. So then internal bypass, the FET is gonna be closed in the charger device in the sink. So then the B bus is gonna be connected to direct to the battery cell of the sink device. So this is for better efficiency, like above 95%. It's not consuming by the switching charger inside the sink device. So this gonna help for direct charging. So that I'm sorry. That's why the PPS programmable power supplies helps to direct charging controls. So we have the reference website and the product website. So there are a lot of information for our the reference board. Also, the all these schematics are uploaded in the website, so anybody can access to there. So this is all that I have. So if you have any questions.
So thank you, Andrew, for your interesting presentation. I think now we can just take a look at the questions from all of you. So maybe we can just start with the first one. When you create the reference board, how do you choose all the passive components such as inductors and capacitors? Any reason to use different company parts?
Actually, when we develop the reference board, we calculate the required inductance and the capacitance value based on our circuit. And then we looked at some of the vendors like DSKey or Mouser. And so, and we also consider if it is for automotive qualified or its industrial part. So depending on that, we choose the one of the best ones. So if in inductors, we've been using many the built parts. So that's the way we do.
Okay, great. So there's another question. How many times do you revise the reference board usually? And what makes the board need to be fixed? Is it because of part issue or PCB layout?
When we actually we did twice this PCB, the reference board revision, because it's for both the schematic issues and then the PCB layout. So mostly it's for schematic. Sometimes it's some circuit is missing, like you know, if there is a I2C the interface, then the I2C translator is missing or something like that. So then we revise the reference board, but not many times for the part issues. I believe all the parts work good.
Okay, great. And there's one last question. Do customers use the same parts used in the reference board in their own applications?
It depends. Actually, the core parts, like inductor and capacitors, like bulk capacitors. So then they follow as we recommend in the reference board. But if not like a small ceramic capacitors, then I think the customers choose as their own. So probably they're gonna choose the low cost or the different ones they've been using. So I would say the primary parts they follow the customers use the same as it is in the reference board, but the small capacity the parts they don't. That's from my experience.
Okay, thank you. So thank you for your interesting presentation, and now we can finish this. If there are any questions left, we will answer them via email afterwards. Thank you very much for your attention, and I hope you enjoyed our presentation. The next presentation topic is SiC gate driver systems with VE HEDT series, and this will start at 5 p.m. So see you there and enjoy our digital days. So goodbye.